Take a look at the equation sheet for Unit 1. In Unit 1, we basically have two equations that we're going to focus on. So let's take a look at this first one here. Delta x is equal to xf minus xi. This is really just a mathematical definition of displacement. Okay? Displacement, delta x, is really just change in position. Remember, delta or the triangle means change. So this tells us the displacement, also known as change in position. And just like any type of change equation, when we find the change in position, we take the final position and subtract the initial position. And it is important to do it in that order so that you get your direction signs right. A positive displacement tells us that the object is moving towards the positive end of the number line. A negative displacement would mean it's moving back towards the negative end of the number line. And that's important when you're looking at change in position. Now our other equation here, we have v equals delta x divided by delta t. This right here is the mathematical definition of average velocity. It says the average velocity for an object is equal to the change in position divided by the time. Now this is just an average. Okay, really it should have a line over it. The line keeps getting left off when I print this thing out. So the change in position divided by time really just gives you an average, and it's only useful to find the actual velocity if the object is going a constant velocity. If the thing is speeding up or slowing down, you can still get an average by using this equation. You can still find the average velocity by taking the change in position divided by the time. But it's only going to tell you the average. It will not tell you how fast it's going at a certain point in time. And I see a lot of students making a big mistake here in trying to use this to find the velocity of an object given, you know, in a kinetic energy problem where you have a force put on it over a distance and it's speeding up or slowing down. So this is really not that useful unless the object is going at constant velocity. So if you note the thing is not speeding up or slowing down, then you can find the velocity simply by taking that change in position and dividing it by the time. Let's take a look at the equations that we deal with in Unit 2. So in Unit 2, we have basically three equations. And the first one I'm going to look at is this one. It's actually the mathematical definition of acceleration. Acceleration is equal to the change in velocity divided by the time. Now you can use this to find the acceleration of an object if you know the velocity it started at, the velocity it ended up at, and how much time went by. An important point here, because when we find change in velocity, we always take final minus initial. That means when the object loses velocity or slows down, the acceleration should end up negative. If the velocity increases and it gets faster, the velocity should end up positive. This is also directly related to the slope on a velocity versus time graph. We've got a velocity versus time graph here, and we find the slope of a line on there. All we're finding is the change in velocity on the vertical axis and the change in time on the horizontal axis. And then when we find the slope, we're just taking that rise and dividing by the run, which is the acceleration. So you see just from this mathematical definition why the slope on a velocity versus time graph is equal to the acceleration. Another important equation is this nice big long one, which we call the position equation. We use this all the time. So it says that the position at any point in time is equal to an object's initial position plus its initial velocity times its time plus 1/2 times the acceleration times the time squared. And there's a lot of people that end up leaving out that time squared part, but it's important. So the point of this equation is it says, okay, if I want to know exactly where an object is, what do I need to know? I need to know where it started. That's important, because if I don't know where it started, then there's no way to know where it's going to end up. For most cases, we can call the starting point 0, because when we set up an equation, we can say, okay, here's my number line. The origin of my number line is going to be exactly where the object starts. It makes the math a lot easier, and we can just call the initial position 0. But it is important to know that. This next part right here, velocity times time, this basically tells us how far the object moves because of a constant velocity. So the object starts off at a velocity of, say, 30 meters per second. Because it's moving to begin with, it's going to move a certain distance based on that initial velocity and how long the object is moving for. This final part right here tells us how much further the object moves or less far it moves if it's a negative acceleration because it's speeding up or slowing down. So things that are going to speed up are going to move further than they would have if they were going at constant velocity. Things that slow down and have a negative acceleration are not going to move quite as far. We can see if you put in a negative acceleration here, it's actually going to take some distance away from that constant velocity. So basically, this tells us how much extra you gain or how much you lose because of your speeding up or slowing down. And this last part tells you how far you're going to go because of your constant velocity. And of course, if the acceleration here ends up being 0, then this whole part cancels out because 0 times all of that is 0. And you're left with just this part right here, which tells us how far an object goes if it's going a constant velocity. And that makes sense because if your acceleration is 0, then your velocity is constant. The final equation we're going to talk about is this one right here. This is the velocity equation. It says if I want to know how fast an object is going at any point in time, I need to know the starting velocity, so how fast it was going when the clock started. I need to know how fast it accelerated at, how much it sped up or slowed down, and I need to know how long it actually did that speeding up or slowing down. So we call this the velocity equation, and this right here is only going to be 0 if the object starts out from rest. Now, there's a lot of objects that do start out from rest, but not all of them. And too often we get people that are doing this calculation and they just automatically cross that out and say that's 0. But that's only true if the object actually starts from rest. If it's moving to begin with, you need to fill that in. That's the initial or starting velocity. Technically based on the unit, it's actually the velocity at time 0, but that's the point. That's how fast it's moving when you start analyzing the subject. And we can see here, based on that starting velocity, if our acceleration is positive, then when we multiply by the time, we're going to add these together, and we'll get a bigger and bigger velocity as time goes on, so the thing will be speeding up. If the acceleration is negative, then when we multiply by the time, we're going to get a negative part, and it's going to add that velocity and actually take away from it. It will be slowing and slowing down. So these two equations here, the position equation and the velocity equation, are very important kinematic equations. And they can be used to figure out a lot of different things about objects that are moving. And as we'll see in Unit 3, we're going to connect all of those different things using the acceleration, which we'll figure out from the force diagrams. Unit 3, we actually only have a couple of equations. We've got this one and this one. So the first one, F equals m times a. We call this Newton's second law. And oh, how many times I've said, what is Newton's second law? And people go, it's an equation. And the way Newton set it up, actually, was he said, I want to know how fast an object is going to accelerate. Well, what is that going to depend on? It depends on how hard I push on it, so the force, and it also depends on the mass. But it's a relationship, it's a ratio. When I look at how hard I push on it, the harder I push on that object, the more force I put on it, the bigger the acceleration is going to be. But if I increase the mass, I increase the inertia. Remember, inertia is just an object's tendency to not want to change its motion. And so the bigger the mass, the less the acceleration is going to be. So this is the way Newton actually formulated it, but we write it as F equals ma, so just for ease of memorization. And one thing we need to remember is this really should be the net force. So you have to take into account all of the forces that are working on an object. If there's a force of push, but there's friction, those forces are going to try to cancel each other out. And whatever's left over, if any, I mean, if they're completely balanced, then there will be no acceleration because the net force will be zero. But if there's a little bit left over, either by the friction or by the push force, then that force can cause an acceleration. And so there's another way to look at it. If there is any acceleration on an object, if it's speeding up, slowing down, or changing direction, remember those are three ways that there can be an acceleration, that means there has to be some sort of net force on the object. And so it can be a way to determine, is there something pushing on that object or not? Is it speeding up or slowing down? Yes, there has to be a net force. If not, then either there are no forces or the forces are balanced. Either way, the net force is zero. Okay, the other equation here is for calculating frictional force. It says if I want to know how much frictional force there is on an object, I need to know what its normal force is. And I need to know what the coefficient of friction is between it and the other surface that is involved. So the bigger the coefficient of friction, the more the two surfaces are going to stick together, the harder it's going to be to move. So the more frictional force there's going to be. But we also get an increase in friction if we increase the normal force. Normal force describes basically how much that object is pushed into the surface, whether it's the floor or the ground, or it could be on a wall as well. But anywhere there's contact and you have a normal force, the magnitude of the normal force here tells us how hard those things are pushed together. You can increase the frictional force on an object just by changing how much those surfaces are pushed together. And so those two things can be used to find that frictional force. And that's going to be important on your force diagrams. Because remember, I'm not going to tell you what the frictional force is. I'm going to give you a coefficient of friction. And you're going to have to multiply that by the normal force. But you're only going to be able to do that if you know what the normal force is. And that's why it's good to draw your force diagrams and make sure you label all of your forces. Look at the equations that we used in Unit 4. Unit 4 was all about gravity. So we got three equations. This one, and this one. So the first one, Fg equals big G times m1 times m2 divided by d squared. This equation is used to find the force of gravity between any two objects. Now there's a couple things that you need to know to find that force. You need to know the mass of each object, so that's what m1 and m2 are. And it doesn't matter which mass you put in there because you're just multiplying them. So as far as the order of masses, it doesn't really make a difference. But you also need to know how far apart their centers are, because this distance here is based on how far apart the object's centers are. Now some objects are small enough that we don't really have to worry about are we measuring to the center or not. So if you're going to find the gravitational force between like a baseball and a football, there's not much of a difference between how far apart they are and how far apart their centers are. But when you're talking about planets, there is a huge difference between measuring to the edge of the planet and measuring to the center. So we do need to keep in mind that this really has to be the distance between their centers. And forget that in that equation, that distance is squared. I see a lot of people getting this wrong because they just divide by the distance. You have to square the distance first and then divide. The other thing here is big G. Big G is the universal gravitation constant. It has a value of 6.67 e to the negative 11th, and that's newtons times meters squared per kilogram squared. Okay, I get a lot of people that get mixed up, and they think that this is some sort of equation, and they're trying to put forces and all kind of stuff in there. But these are not symbols; they're units. They go along with to give us the value of this 6.67. 6.67 times 10 to the negative 11th what? newtons times meters squared per kilogram squared. It has those crazy units so that it works out with units of the other measurements for mass and distance. This is the universal gravitation constant. It works everywhere in the universe. And that will be listed on the back of your equation sheet. The next equation, get rid of this stuff, is W equals M times G. This is the shortcut equation for finding the weight or the force of gravity for an object here on Earth. Because you need to realize weight and force of gravity mean the same thing. So you can write here, Fg equals lowercase w for weight. Force of gravity and weight are the exact same measurement. They're just two names for the same thing, like car and automobile. Okay? So in this equation, we want to find the weight of an object. We multiply its mass times little g, which is the acceleration due to gravity. Now this is a shortcut. We could use this big equation down here to find the force of gravity between an object and the Earth, but you're going to have to know what the radius of the Earth is and the mass of the Earth. That can be kind of a big equation to do all the time. And so we have this shortcut. We know that all objects have an acceleration of 9.8 meters per second here on Earth. So if we want to know the weight, we can actually just take the mass and multiply by 9.8. But it only works here on Earth. This value right here is the acceleration due to gravity on Earth. And you can use this same equation on the moon or on Mars or something like that, but G is going to have a different value then. G will have a value on the moon of about 9.8 divided by 6, about 6 times less. So you can use the same shortcut equation, but you would have to know what that value is. Because most of the things that we look at operate here on Earth, we are going to use that most of the times just to find the weight if we know the mass and the acceleration due to gravity. Our last equation, V squared equals G, big G, times M divided by R. This is the equation to find orbital velocity. It can only be used to find the velocity of a satellite. I've seen people try to use this to find the velocity of a car driving down the road, and it doesn't make any sense. You need to know what the equations are for and where they can be used. The only place that this equation can be used is for finding how fast an object has to go to stay in orbit around a planet or a moon or something like that. In this equation, we have 1m. Now, of course, m stands for mass, but don't get confused. Remember that these objects that are in orbit are free-falling. Their actual mass doesn't matter. What matters is the mass of the planet or the moon that is being orbited. So this is the mass of the object being orbited. So if they give you the mass of the satellite or the astronaut or whatever is going around, or if you're looking at a moon going around a planet, the mass of the moon or the satellite or the astronaut, it doesn't matter. Those things are in free fall, and they'll all accelerate the exact same way no matter what their mass is. But the bigger the planet, the more massive the planet that's being orbited, the more gravitational pull there is and the more velocity you're going to need. G, just like in our first equation, is the universal gravitation constant. So we use that again. That's the 6.67 e to the negative 11th newtons times meters squared per kilogram squared. And then we have R. R is the radius of the orbit. So if you think about it, you've got this planet right here, and you've got this moon or satellite or something going around. It has to be the radius of the orbit. Well, that's going to be this right here. All that really is the distance between the center of the planet and the object that's doing the orbiting, that is the satellite. So really, we can just use the distance between the planet and the moon, or the planet and then the space shuttle or whatever as our radius, but technically it stands for radius of the orbit. Another thing to remember, in this equation, it's v squared equals this stuff. So if you're going to solve for orbital velocity, you first multiply big G times m, divide by r, but that is not where you stop. You then have to take the square root of each side to cancel out that squared part right there and actually get the velocity. One more reminder, this equation is only used to find the orbital velocity of something that is a satellite. Okay, let's talk about the equations for Unit 5. Unit 5 was all about momentum. And so we have three equations that we learned. This one, and this one. So let's talk about the first one. The first one is really just the definition of momentum. Momentum equals mass times velocity. Now that's pretty simple. But the thing that a lot of students get screwed up on is a question will ask you to find the velocity of an object. And they go, well, how am I supposed to find that? Well, if you think about it, if you can somehow find the momentum of that object through other means, if you know the impulse imparted to it or something like that, or there's a collision and you can find a transfer of momentum, well, if you can find that momentum and you know the object's mass, you can simply divide to find its velocity. And really, that's where momentum is useful. Yeah, it's easy to calculate momentum, multiply the mass and the velocity, but usually what we want to know is, okay, if I find out that the object gets a certain amount of momentum, what does that mean for how fast it's going? How fast can I predict it will be going once it gets that momentum or once it loses some momentum? So that's where this equation is really useful. One thing to remember here, the units for momentum, we actually have two different units that we can use. Just based on our equation, we can use simply kilograms times meters per second. That's an acceptable unit for momentum. But of course, this has an equivalent in newtons times seconds. Remember, those two things mean the same thing. They're equal to each other. They're just two ways of writing the same thing. And that's because a newton is really a kilogram times meter per second, if you remember. All right, let's take a look at our second equation. And that's this one. This is the equation form of the law of conservation of momentum. Remember that sigma stands for sum of, or total, or net, however you want to say it. Basically, it says the total initial momentum, that's why we have this I with the P, the total initial momentum has to be equal to the total final momentum. But this is only true if there are no outside forces or changes in shape of objects. Remember, those are two situations where momentum is not conserved, and the total momentum before and after will not add up. So if there's any outside forces, gravity, friction, anything that is going to either take away or give momentum through a force acting, then momentum will not be conserved. And if there's any changes in shape, then there's going to be energy loss, and momentum is not conserved in those cases as well. So this equation is mostly useful for looking at what happens in a collision, whether it's an inelastic collision or an elastic collision. Now, there's different ways you can write this out with terms based on whether it's an elastic or an inelastic, but it's all based around this equation right here. So let's say we had two objects. Well, the sum of the momentums just means we have, object 1's momentum plus object 2's momentum. So before anything happens, each of these objects have their own momentum. Now, one of them could have a momentum of 0. They both might have positive momentums. Maybe one's got a positive momentum. Maybe one's got a negative momentum. It doesn't matter. When we add those two momentums together, they have to come out to whatever the total momentum is after the collision. Now, after the collision, there's a couple different things that could happen. Maybe the two objects stick together. In that case, there's just a total. momentum because there's only one object. Once the two objects stick together, there's no two objects anymore. You got one object, but of course it has a mass that is equal to the two masses added together. But maybe instead of sticking together, they bounce apart. In that case, there are two other objects again, and then we just have to have their momentums on this side. But the point is, this is before or initial, and this right here is after. And you need to set them up those ways. On the momentum test, a lot of people got confused in the situation where you have a guy sitting down and he throws an object. In that case, the initial momentum is 0. So the guy's sitting there, he's holding something, neither object is moving, they don't have any momentum to begin with. That means after he throws the object, there's no outside forces like friction or gravity, and we're assuming there's not here, the total momentum still has to add up to 0. But obviously both objects are moving. The only way that can happen is if one object is going in the positive direction and one object is going in the negative direction. It would mean one has a positive momentum and one has a negative momentum. But they have to have the same magnitude. That means if one object's momentum is 60 Newton seconds, the other one's momentum has to be negative 60 Newton seconds. And some people were able to work out that, oh, they have to have the same momentum, but a lot of people have screwed up the fact that they have to have opposite directions and left that negative part out when they were calculating the velocity of one of the objects. So think about that. For the total momentum to add up to 0, which is what it was to begin with, they have to have momentums in the opposite direction. Let's move on to our last equation here for Unit 5, and that is the impulse equation. It says that when you put a force on an object over a certain amount of time, that changes the momentum of the object. And this is the one that a lot of people struggled with on the egg drop project. If you drop an egg or anything from the top of a building, there is an outside force there. It's going to pull the object down until it hits the ground. When it hits the ground and there's that collision, there is going to be an impulse that is provided by the ground. The ground pushes on the egg to stop it. Of course, the egg pushes back too, but that's not what we're worried about. We're looking at the egg. The egg's momentum has to change. How much is it going to change? Well, how much did it start with? Let's say it started with 50 Newton seconds of momentum. In order to stop the egg, the ground has to take away all of that momentum, every bit of it. It can't have any momentum left if it's going to stop. That means the change in momentum here has to be negative 50 Newton seconds. We're taking all of the momentum away. So the force applied depends on how much time there is, because the product of those two things has to end up being negative 50. Now, the direction of the ground pushing on it, that direction is going to be negative, so we have a negative force, but it could be anything. We could have negative 5 newtons times 10 seconds. That would give us negative 50 Newton seconds. We could have negative 50 Newton seconds for 1 second. That would also give us negative 50 Newton seconds. We could have negative 100 newtons multiplied by 0.5 seconds, half a second. That would still get us negative 50 Newton seconds. But you can see, as we decrease the time, the force necessary to get negative 50 Newton seconds goes up and up and up. And conversely, if we want to decrease the force, as we did on our egg drop projects, we want to increase the amount of time. And that's what your objects were supposed to do, your egg drop projects. You're supposed to increase the amount of time that the force was applied and stop the egg without putting enough force on it to break it. But it's all based on this idea of a change in momentum. Another way that you'll be asked to probably use this equation is to go, okay, I push on an object with a certain amount of force for a certain amount of time. How fast does that object end up going? Well, we can figure out the impulse just by multiplying the force and the time. Let's say we push on it for 10 seconds with a force of 2 newtons. That means the impulse here is 20 Newton seconds. That also means that the change in momentum has to be 20 Newton seconds. The impulse and the change in momentum, they're the same thing. So if we know the momentum changes by 20 newton seconds, then we can put that with whatever momentum the object started out with. Maybe it started at a momentum of 0, is sitting still, so it would end up with 20 newton seconds. Maybe it started with a momentum of 100. You'd have to calculate that from the mass and the velocity, but if it started out with a momentum of 100 and the impulse or the change in momentum was 20, you would end up with 120 newton seconds. So you have to take into account what the momentum started at. Only use 20 newton seconds for your final momentum if it actually started with a momentum of 0. Once you figure out the final momentum, whatever it is, let's say it's 20, 120, 500, it doesn't matter, you can use that first equation to figure out how fast it's going. Because if you know that this thing started with 100 newton seconds of momentum, it gained 20, the final momentum is 120 newton seconds. If you know that object's mass, you can divide and find out how fast it's going. Unit 6 equations. So in Unit 6, we had a few equations. We had this one, this one, this one, this one, and this one. So actually 5 total equations. Let's look at the first one. KE equals 1/2 m times v squared. This is the kinetic energy equation. It lets you calculate the amount of energy an object has because of its movement based on its mass and its velocity. This isn't too hard of an equation to use, except you have to remember that the velocity here is squared. So when you put it in to find the energy, you got to make sure you square the velocity, take half the mass, and then multiply. Remember your order of operation. But really, the way we want to use this is if we know how much kinetic energy an object has, we should be able to calculate the velocity. That's really how this is useful. So we know, okay, an object has, say, 500 joules of kinetic energy, and its mass is 10 kilograms, something like that. We should be able to find its velocity from that information. The one thing that students get tripped up on sometimes is forgetting that square. So when you solve this, let's actually do that. 500 equals 1/2 times 10 times v squared. So half of 10 would be 5, and then we're going to divide by 5 over here, and we actually get 100 equals v squared. And a lot of students stop right there. And realize this doesn't tell us the velocity, it tells us the velocity as a square. So to cancel this out, we actually have to take the square root of each side. And we get that the actual velocity here is the square root of 100, which is 10 meters per second. So that's really the most useful way to use this equation. The next equation is the work equation, and it tells us that work is equal to force times the distance. This is a pretty simple equation to use. Sometimes you're going to have to, based on the work done, if you know the work done, you're going to have to calculate how far the object moves or how much force was causing that work to be done. This is a fairly straightforward equation, but we also need to remember that work is also equal to the change in kinetic energy. And that's important to understand. Now that's not an actual equation on here, but it's a theorem. It's called the work energy theorem. And we use that in conjunction with the actual kinetic energies of an object to figure out what's going on. So basically, when you calculate the amount of work done to an object here, that's how much the energy of that object changes. Now, if you have a positive force pushing in the direction that the object is already going in or is going to move in, then the work done is going to be positive, and the change in kinetic energy is going to be positive. The object is going to gain that kinetic energy. If the force here is negative, and that's going to happen if the net force is in the opposite direction that the object is moving, then that is going to take energy away. And so the work done is going to be negative, and the change in kinetic energy is going to be negative. And in that case, that net negative force is actually going to slow the object down. The next equation that we have is the potential energy equation. So here we have GPE equals weight times height. Gravitational potential energy is equal to an object's weight times how high it is above the ground. The gravitational potential energy, remember, is based on how much work gravity is going to do as the thing falls. The one thing that you really got to be careful about is that this is weight, not mass. In a problem, it's just going to tell you what the mass is. It'll say, oh, a 10-kilogram object is so far above the ground. But you have to calculate the weight. So moving back to an equation we used in another chapter, weight equals the mass times the acceleration due to gravity. You've got to use that and calculate the actual weight of an object based on the mass and the acceleration due to gravity, which is 9.8. So take the mass times 9.8, and then we can put that into the equation as the weight and figure out what the gravitational potential energy is based on the height. Okay, the next equation here is ME equals GPE plus KE. And this is the equation for mechanical energy. The mechanical energy of an object just basically describes what the total amount of energy it has, as long as there's no forces other than gravity that are working on it. So it's going to be equal to the potential energy and the kinetic energy added together. We usually see this in a case of an object that is dropped. We can use it for roller coasters as well, though. So for a roller coaster, it starts with a certain amount of potential energy. As it goes down, that gets converted into kinetic energy. And then as it goes back up, it'll get converted back into potential energy. But during that whole time, as long as there's no significant friction, these two things added together should always equal the same amount. So this mechanical energy, as you're dropping the object or as it's going up and down the roller coaster, if there's no significant friction, there's no energy losses, then that mechanical energy should be the same all the way down. And so at any point, if you know the potential energy based on the height of an object, and we can usually calculate that, and the mechanical energy has to be a certain amount, well, then we can just subtract to find the kinetic energy. And why would we want to do that? Because if we know the kinetic energy, then we can use the kinetic energy equation and figure out how fast that object is going. So in this case, usually what you're going to do is, okay, it starts out with a certain amount of potential energy, and it starts out with zero kinetic energy because it's dropped, or it actually could start with some kinetic energy. But the point is, you would figure out those starting amounts. That has to be the total amount of mechanical energy, and as long as there's no friction, that shouldn't change. And this is useful for an object that is dropped, or like I said, a roller coaster, a ball going down a ramp, whatever, as long as there's no friction. And if you find the height, or the potential energy based on the height, then you can find the kinetic energy and figure out how fast it's going at that point. And then the final equation for Unit 6 is pretty simple. Power is equal to the change in energy divided by the time. Now, a lot of people in Unit 6 got this mixed up with momentum. Remember, momentum is a lowercase p, but also momentum doesn't really have anything to do with energy transfers. And here, delta is change, remember, so this is the change in energy divided by the time. It basically just tells you how fast the energy can change, how quickly you can get energy from one sort into another. So for example, from electrical energy into heat energy or into light energy. But usually the way we're going to see it is in the terms of work, because remember, work equals a change in kinetic energy. That's a type of energy change. That means if we want to figure out the power for an object and we know how much work is done, we can simply put work in to that equation, divide by the amount of time, and figure out what the power is. In some cases, what we want to do is, based on the power, we want to figure out how much the energy changes based on the amount of time that it takes. And so we'll multiply the power by the time to find that. Unit 7 equations. We've actually got quite a few equations from Unit 7. So we've got 1, 2, 3, 4, 5 different equations from Unit 7. First one, pretty simple. The temperature is equal to the temperature in degrees Celsius plus 273. This is simply just a conversion between Celsius and Kelvin. So the Kelvin temperature We take the Celsius temperature and add 273. Pretty simple. The next equation, this one right here, we got P1 times V1 over T1 equals P2 times V2 over T2. This is called the combined gas law. The point of this equation is to figure out how these different variables, pressure, volume, and temperature, are going to change in a given situation. In some cases, all three of these things will be changing, and you'll fill in numbers for each one of them. In some cases, something will stay the same. So let's say the volume stays the same. If the volume stays the same, then we know that any volume that we put in on both sides will simply cancel each other out. So the simplest thing is just to put a 1 in for each of those. Some people think about just leaving them out, and that's all right, but just realize you're not putting a 0 in. It's because it's canceling each other out. We can just ignore them multiplying by 1. When you set this up, the best way to solve this problem is to cross multiply. And we can actually even rearrange this in terms of that. So if we cross multiply, we take P1 times V1 times T2, and that is equal to, if we cross multiply this way, T1 times P2 times V2. And that's a way to kind of rearrange it and get that temperature off the bottom. It's really important if the temperature is one of the things that you're solving for, because I've seen so many times that this is our unknown right here, that people set this up and then they divide the absolute wrong way and get a temperature that doesn't make any sense whatsoever. So be careful about that. You need to cross multiply so that you get that off of the denominator. The next equation right here, change in length is equal to alpha times the original length times the change in temperature. This equation is fairly straightforward. A couple of things. This alpha value, of course, stands for the coefficient of thermal expansion. Basically, it's a value you look up for the type of material you're talking about. So if it's copper, you look up copper's value. If it's steel, you look up steel's value. This is the starting length. The equation tells you the change in length, and you have to be careful about that. If the problem asks you, how long is the object now, or what is the new length of the object, when you do this calculation and you get an answer out, you're just going to get the change in length, and so then you have to add that to the original length. The change in length should be negative if the object is cooling down. It should be positive if the object is heating up, because that's going to tell you whether it gets bigger or smaller. You won't get those wrong as long as you do your change in temperature correctly. Remember, change in anything, in this case temperature, should be the final temperature minus the initial temperature always. So that if you have something that is cooling down, where the final temperature is bigger than the initial temperature, you'll get a negative answer here, and when you multiply that through, you'll get a negative change in length, which makes sense. Okay, the next equation is the equation for heat. Heat, or change in thermal energy, two terms for the same thing, is equal to the specific heat multiplied by the mass multiplied by the change in temperature. Now, we just talked about how change in temperature always needs to be final minus initial. That's important in this case as well. The mass here, pretty straightforward. The specific heat is another value that you look up out of a table. You have to make sure you choose the right one, though, and don't look at the wrong table. Don't get specific heat confused with heat. This is the energy that is going to be transferred for the object. Now, if this thing is increasing in temperature, Q here should be positive, because the energy input is going to be positive. If the thing is decreasing in temperature, that means energy or heat is flowing out of the object, and Q here should be negative. We generally see this in conjunction with thermal equilibrium problems, where you have two different substances and you set it up as Q equals M times C times TF minus TI. I'm just going to cheat and copy that right over. So I made another table there. But the point is, we have two different substances. One of the substances is going to start at a higher temperature, And so that one has to have a negative cube. And when you start doing these problems, you'll put them together, and the only way you can do that is if you take out that negative sign by multiplying the entire equation by -1. And then the final equation is the one for pressure. Pressure equals force divided by area. Now, a lot of people get confused here because area is measured in meters squared. All that means is meters times meters. And you get that because if you think about taking the area of a rectangle, let's say the area or the lengths here are 2 meters and 1 meter. When you multiply those together, you don't just multiply the numbers, you multiply the units as well, and you get 2 meters times meters, or 2 meters squared. That doesn't mean that you take an area. For example, if I were to give you an area of 10 meters squared, or sometimes we say 10 square meters, that doesn't mean you take 10 and square it before you put it in the equation. No, that's just, that square goes along with the units, not with the whole number. You got to be a little bit careful about that. Also, force here, if we're talking about a solid object sitting on the ground or on the snow or whatever, the force is going to be the weight of the object. And of course, weight equals mass times the acceleration due to gravity. A lot of people forgot that on the test. You have to multiply the mass by 9.8 and then put that into the equation, divide by the total area to figure out what the pressure is. Pressure, of course, is measured in pascals. Also, don't forget how many feet, tires, whatever the object that you're looking for the pressure has, because if a single tire has a certain area and there's 20 tires, well, then you're going to have a much lower pressure because that area is spread out much bigger. And you have to take that into account when you're calculating the area. So you take the area of a single tire and multiply it by how many tires there are to figure out the total area. Okay, in Unit 10, we only had one equation. It's this one right here. NF equals NI times 0.5 to the power of T minus T1/2. Okay, so let's take a look at each part here. The N here stands for any number. Now, the reason why we have N in here instead of something like M for mass is because you can actually use this equation for, let's back. Now, this equation is our equation for radioactive decay. Specifically, it tells us how much radioactive material will be left after a certain amount of time goes by, based on how much you started with and the half-life of the material. So this N right here stands for any number. And we have it that way versus like putting something like M in there for mass, because we can start with a certain amount of material, say 50 kilograms, or we could start with a certain number of atoms. We could start with 1,000,000 atoms, or even a percentage. We could say, okay, that's 100%. What percent is going to be left? So that's why we have it a little bit more vague and a little bit more general, is because you can actually put different things in there. So you got to be a little bit careful about that. The way it's set up, if you're starting with a certain amount of mass, a certain amount measured in kilograms, then when you do the equation, you're going to get out how many kilograms are left. If you start with a number of atoms, you're going to get out how many atoms are left. If you start with a percentage, you're going to get out how much of the percentage you're going to have left. So that's why the equation is set up with those ends like that. So this is the initial amount, this is the final amount. And specifically, this equation does tell you how much is left, not how much goes through the radioactive decay. To figure that out, you have to first calculate how much you end up with. Let's say you start with 100 atoms and you end up with 80 atoms. If you want to know how many have gone through, well, then it's just a simple subtraction. Figure out that there's 20 that have actually flipped and gone through the radioactive decay. Now, the other big part of the equation is this ratio up here. T over T1/2. T is time. We're used to that. T to the 1/2 is the half-life of the material, which tells us how long it takes for half of the material to break down. The ratio of these two things, when you divide the time by the half-life, that tells you the number of half-lives that have gone by. Now, sometimes that can be nice ratio that gives you an integer like 2 or 3 half-lives have gone by, but most of the time you're going to get a decimal. When you divide these, you might get that 6.259 half-lives have gone by. And that's okay. The equation is set up so that we'll use it whatever way. The big thing you have to be careful about is making sure that both of these have the same units. You can't take time in days and divide it by a half-life in seconds and have a ratio. It's supposed to be a simple ratio without actually any units. And to not have any units, that would mean you'd have to have seconds and seconds so they cancel, or minutes and minutes so they cancel, or whatever. But it doesn't matter actually which ones you have as long as they're the same. So a lot of times you're going to end up having to convert either the half-life or the time that goes by so that you do have the same units there. The other thing that you have to be careful about, of course, is not getting these mixed up. And I'm not sure why. It seems like people mix them up all the time. And you have the half-life divided by the time that goes by. You need to really think about that. Make sure you're putting them in the right places. Now, when you get that simple ratio, let's say you get a ratio of exactly 2, just for the heck of it. That means you're taking 0.5 to the second power. You're squaring it. If you get a ratio of 2.86, you're taking 0.5 to the 2.86 power. This is where that answer button really comes in handy when you're doing problems on your calculator, because you can take this simple ratio and you may get some really long number. You might get 2.49837256, blah, blah, blah. You can actually just take on your calculator and push 0.5 and then the caret to take it to a power. So I'll write that down here, 0.5, and then press the caret button and then hit answer, that ANS, and that'll put the previous answer in from that ratio. Then once you've taken 0.5 to whatever power that is, you get that number, you multiply it by the initial amount, and that tells you how much is left.